Hey, welcome to video 10.2 where we're going to be looking at collisions. This is going to be the single most important application of conservation of momentum, so we'll spend the next couple of videos on this topic. And we'll define a collision as a short interaction between two or more objects, short being the important thing. So there's some well-defined initial condition of the system, then some interaction, then some well-defined final interaction. And we'll see that in any collision, the momentum of the system will be conserved, which means, well, it arises from the fact that the interaction is very short. So delta t is small. And also in a collision, you'll find that the internal forces are large, and we'll treat external forces are small, or at least normal sized. But because delta t is so small, the impulse due to external forces is going to be very small, and that means that momentum will be conserved. Because the internal forces are large, what will happen is that the momentum of each part of the system might change, but the total momentum of the system will be constant. And so what we'll do is we'll say, okay, the initial momentum is the sum of the initial velocities, or the sum of the initial momenta individually. Come on, computer. And the final momentum is the sum of the final momentum. Now, whenever you have a collision, momentum will always be conserved, but energy will not always be conserved. So for instance, there are some definitions here. A perfectly inelastic collision is when two objects stick together. And when this is the case, the final velocities are equal. It's called perfectly inelastic because we find that it loses more energy that way than in any other possible collision. An inelastic collision without the perfectly attached on the front is one in which kinetic energy is lost. So the initial kinetic energy is greater than the final kinetic energy. And an elastic collision is one where the initial and final energies are conserved, or equal, so energy is conserved in addition to momentum. Generally, elastic collisions are the most difficult ones to deal with mathematically. So for our example, let's say that we have a 3.5 gram bullet fired horizontally at 2 blocks at rest on a frictionless tabletop. So our initial condition is you have block A, which is stationary, and block B, which is also stationary, and a bullet of mass m moving with speed v. The bullet passes through the first block and then embeds itself in the second block. So there's a hole through block A now, and block A is moving at 0.63 meters per second. And the bullet embeds itself in block B, so that now effectively has the mass of B plus the mass of the bullet m, and that's moving at 1.4 meters per second. Now, because it's a frictionless tabletop, that means that the external force due to friction is 0, and so the only horizontal forces in this system are internal, so momentum will be conserved. And what we want to find is the initial speed of the bullet before it enters the first block. So we'll say that the initial momentum is just the mass of the bullet times its velocity. Neither block is moving initially, so they have no momentum. Afterwards, the final momentum of the system is the mass of block A times its velocity, plus the mass of block B and the bullet, times their velocity. Because they're both moving the same direction, we add them. But remember, momentum is a vector, which means that if somehow block A were moving to the left, we would have to make its velocity negative. And we set these two equal, and then we solve for V, which ends up ma times Va plus mb plus m Vb all over the mass of the bullet. Now in practice, we probably don't need to add this mass here because it's so much smaller than the mass of block B, but we will anyway. And when we plug the numbers in, we find that the bullet was moving with a speed of 937 meters per second. So that is a very, very straightforward problem. A lot of the conservation of momentum stuff will be like this, but we'll see in the next video that it gets a little trickier sometimes. But first, we want to establish, was this an elastic collision, or was it an inelastic collision? And so to do this, we have to calculate the initial kinetic energy and the final kinetic energy. Now the initial kinetic energy is just the mass of the bullet times the square of its velocity. And we'll get a number that is equal to, let me get my calculator, (1,536 joules). Now we'll also have to find the final energy of the system, and if that happens to equal the initial energy, then they were elastic collisions. And if it happens to be less than the final energy, then it was an inelastic collision. If it's greater than the initial energy, then it probably means we made a mistake somewhere. So you 1/2 times the mass of block A times its velocity plus the combined masses of the bullets times the square of their velocity. And this works out to okay. Works out to only 2 joules. So it is a highly inelastic collision. Something like 1,530 joules was lost. Now where did that energy go? The answer is that it went in to boring holes through the 2 blocks. It went into breaking things, basically. Because the bullet had to exert a force over a distance to make that hole through block A, and also to embed itself in block B. Also, the bullet's likely to be highly deformed, and in general, when collisions are inelastic, things break or bend, because that's where the energy goes. So the more inelastic a collision is, the more likely you are to get hurt or things are to get broken. That's why, for instance, if you get hit with a baseball, it's going to hurt, but it's probably not going to hurt you very much because there's not that much energy involved. Whereas if you get hit with a bullet, which carries approximately the same momentum as a thrown baseball, it might kill you because its energy is so much higher than the baseball's energy. Now, for tomorrow, I'm going to check questions 3 and 5 from chapter 10.